Okay, so yesterday we went over some of the theorems and results we have here. These are mostly the preliminaries for this final draft of the infinitesimal calculus of the Dirichlet product. So today I noticed actually, so the general plan is we're going to start on our third section, which we'll get straight into power series. And we'll try to work out some proofs there, to work out some final drafts of proofs. Although before that, I noticed that one of these proofs has an error. It is, I think, this one actually. It doesn't make sense. We're presupposing the limit right here. So our proof is that we want these two sequences to have conditional convergence on one another. So one is convergent if the other one is convergent, and vice versa. But we've actually presupposed this limit here. This might make sense as a proof if we had it after, for example, this proof would easily prove this one, and this one also is used to prove this one, but that's circular. We can't have both of these proving each other. So we're going to edit this corollary. We're going to turn it into a theorem. It's going to be a little longer, but it won't be too complicated, hopefully. Yeah, so we're going to start by, I'll find where this is. Oh yeah, let me turn on, actually. I can turn on my full screen share for this. So I have over in the left side, I have the code that I'm writing, and on the right side is the compiled LaTeX. That's the presentation. So over on the left side, we'll be writing the actual stuff, and it'll appear on the right side when we compile it. So first we want to take this, I believe it's this one here, I want to move this somewhere else. We're going to actually move it, I think we're going to put it before this theorem, and we're actually going to state it, I think, as, we could state it as a corollary to this previous one. So if I had it as that, then we would have, yeah, so we have this theorem gives us our cancellation function, and if we wanted to put this corollary here, this would be a corollary to this one. We don't have to do that. This one isn't stated as a corollary either, but we can just turn this whole corollary into a theorem itself. So I'll rename this environment theorem instead of corollary, and it'll get its own theorem number. And we'll have to prove it without using this theorem, I think. But that's okay, actually. In fact, the flow might be a little better if we have this result first. So what we're going to do is going to be similar to how this theorem 2.3 is structured, is that we're going to follow this sort of scheme where we set up the cancellation formula and then we just do an induction. It's going to be the same thing, and actually we can probably copy most of this theorem here. I wonder if maybe not. I was trying to think if maybe one of these theorems could be made easier by the other. I think that's not going to happen though, and the reason is we don't know whether or not this space X is going to be a sequential space. We want to state that these functions have this dependency on one another for their continuity. If X was a sequential space, and we knew in advance that these sequences, maybe we could make them more general. Instead of just having coefficient constant C, we could use some general function G. We could probably use this to prove this in advance, but we don't necessarily know that. Yeah, so I think we can't do that. We just have to do it the long way, and that's okay. So what we're going to do is we're going to make the same sort of observations. So so we have actually it's much of the same structure. So again, we'll probably actually restructure this. So given that this one is first, we'll restructure this theorem to reference the methods of this first one. So we'll actually copy a lot of this. So this primary gets the first direction. So of course, if this xn sequence is convergent, then of course this other sequence will be convergent because we're just multiplying by some constant. Oh, hi! Welcome to the stream. Yeah. So so I don't know if you heard my beginning part. We're updating this theorem, or this was originally stated as a corollary. So if this xn sequence is convergent, if and only if the cxn sequence is. This was originally stated as a corollary to this more general one, but then I realized that there was a small amount of circularity in how the theorems were proved. So I'm going to have to pull it out and do a full proof, a full sort of independent proof of this. Yeah, so we're going to, okay, so we've got the initial part, that's a base case, the first forward direction, simple. And then for the other direction, we'll suppose we'll do C x of n is convergent, so and what we're going to do is, just like in this other proof, we're just going to observe that, yeah, it's going to be the same induction actually, in fact. Right, so notice that, so C x sub n is proportional to C for all n, since C is non-zero. So remember, proportional to just means that can be divided by. That's sort of what it means. So Cxn can be divided by C. We can cancel that off, especially because C is non-zero. So this lets us use the cancellation formula. X sub n equals Cx sub n, cancel C. And we actually want to put these in parentheses like that. So that's coming out right here. I like to try to fit my, there, yeah, that's nice. I like to try to fit all my sentences on nice, neat lines. Don't like to have any little orphans trailing down at the end. So we're gonna apply the cancellation formula on each projection. And so the way that we're gonna set that up is we're gonna just go right over here. We're gonna copy the entire cancellation formula, and we're just gonna slap it right back in, and we're just gonna change all the sort of object names as needed. So let's see. So down here, so this is our general cancellation formula. And so we're just going to do a replacement. We want x divided by y. That's the cancellation that we're calculating. That's going to be x sub n. So whenever we have x divided by y, we're going to replace that with x sub n. And that's there. And it's also right here. So that's the first replacement. And the second replacement is that we need to know what y is. Y is the thing that we're dividing by, and in this case that's c. So whenever we see y, we're going to replace it with c. So we'll have this and that, and also there, and right there. And hopefully I did all that right. Yeah, so this is our cancellation formula now for, oh, I have an x in there. The x is the numerator, which will be c times x of n. X is the thing in the numerator of the cancellation, because this is for x divided by y. So wherever we have x, and I think that's just that one place, we'll have cx sub n. And I think that's it now. Okay. Yeah, so we have xn, which is cxn divided by c. We have our c here, cxn, we have c here, we have c there, xn and c. Okay, so this is perfect. So this is a cancellation formula for when we're canceling c x of n, cancel c, and we're projecting it down onto the k dimension. This is our formula. And then we can just sort of observe by an induction. So we'll do an observation. So we'll say, so we'll have a constant here. This is a constant. This will be continuous. This will be convergent, actually. Instead of continuous, we'll be saying it's convergent. So this is convergent. And then we'll do an inductive premise. We're going to do an inductive premise that these lower indices, these lower projections are all convergent. So by induction, suppose that for each index a less than k, the projection p sub a of x sub n is convergent. This is vacuously true when k equals 1, because there's no positive integers less than 1. So by the above formula, we have written the projection p sub k of x sub n as a composition of sums and products of convergent sequences. And we might want to make, actually, yeah, I think that's okay. So sum and product of convergent sequences and constants. Follows that p sub k, x sub n is also convergent. And by induction, p sub k, x sub n is convergent for every index k. And therefore, x sub n is also convergent. Nice. So pretty straightforward. It's really similar to this other one, and actually because they're so similar, we can now make this one shorter. However, we can also write as a corollary. We have let's see. Let me think. Actually, I think this one needs to be down here. So I want to say, so we know that both of these sequences are now dependently, their convergences depend on one another. We have an if and only if. What we want to say is that once you know that both of these convergence, these things are convergent, dependent on one another, we can also know that, well, if this x sub n is convergent, or if the c x sub n is convergent, then this x sub n will be convergent, and whatever this x sub n limits to, also the c x sub n will just limit to the same thing times c. So actually we can probably put, I think we can actually probably put this one, 2.3.2, we can move this one up as a corollary of this other one. Now, let's see, hopefully that'll fit in nicely. I like to try to fit all my theorems on a single page unless they're really long. Okay, so I think this could maybe be shortened out, but I'm not sure if that's what we want to do. We could also make it longer to put this corollary statement on the next page. So, so C0 is trivial because then it's just a singleton set. So assume C is non-zero. Take any convergent sequence, then this is also convergent, and we have this limit xn goes to L. By continuity of products, C x of n goes to CL, which is in CA. So the limit of our sequence is also in CA. Okay, so I think that's this is fine. This proof it follows really straightforwardly from this theorem. But I do want to change the spacing, so we don't want to have this sort of orphaned preamble to this corollary. So to fix that, I'm actually just going to add some more detail in this theorem 2.2. So let's see. Yeah, so this is fine, I think. So let's beef up this bottom part. So by induction, suppose that for each index a less than k, the projection is of x of n is convergent. This is vacuously true when k equals 1. By the above formula, then, actually we want to update this. That we have each of the each of the projections we'll just list off all the projections in this formula. So we have p sub k z c of cx of n, and we also have this other p sub a of x of n are convergent. Yes. Notice that each of these projections are convergent, and we have written the projection pk x of n as a composition of sums and projects of convergent sequences, of complex convergent sequences. It follows that, actually I think that doesn't matter, we'll just leave that out. It follows that pk x of n is also convergent, and by induction, and maybe we can rewrite this actually in terms of n. Maybe that would be a little nicer. No, that's okay. We have written the projection p sub k x of n as a composition of sums and products of convergent sequences, so it follows that this sequence in terms of n is also convergent. And by induction, p sub k x of n is convergent for every index k. And then we can say, we therefore conclude that this x of n series is also convergent. And that didn't help us at all. That didn't fix our spacing issue. Maybe we'll just add some white space. That always works. 12 is too much. We'll do 5. And I think that'll make it okay. Yeah, there we go. Okay. Blah blah. Each of the projections is convergent. We're in the projection some composition, sums and products, convergent sequences. This is convergent by induction. This is convergent for every index k. Therefore, good. Okay, this all checks out. So it's really similar to this other proof, and actually we're going to update this proof to just reference the fact that we've done this thing. So this is proving this subspace is a closed set. So if we have a limit of things that can be divided by C, then their limit is can also be divided by C. Yeah, and that seems nice. Okay, so now we'll move on to, we'll update this theorem that we wrote to fix that out. Okay, this proof is sequences. So we have yeah, so we'll write, so because, actually, yeah, let's actually, okay, so we'll move these things around. So this is where we start this induction. And we'll move this down below where we state the cancellation formula, just like we did in the first proof. Hopefully that'll make the flow a little better. So proof is similar to the first one. So we'll say, for convenience, let m be the constant value of z of g. Then since this, we have this proportionality here, this is always true, the cancellation formula gives us, and then we have the cancellation formula. So that'll look like, yeah, that'll look like this. And I'll actually move this down here as well. Okay, so m is this constant value, then we have this proportionality, yeah, the cancellation formula. This is the cancellation formula. This should still be good. We haven't changed anything. And then we can just make all these observations. Yeah. Okay, so, and actually we're going to start by noting this reciprocal thing here. So we'll go down here. Since m is this thing, the projection is non-zero, and this reciprocal is continuous. So I'll move this up as the first sentence after the cancellation formula. So this first sentence is noting that this reciprocal is continuous. After that, we can say from here, the proof is similar to the one for convergent sequences. By induction on k in naturals, we suppose that every index has the projection, yeah, we have the projection, P sub A, compose F is a continuous function. Factually true when k equals 1. And then we can just skip this. Since we have written this projection as a composition of continuous functions and operations, so we'll do a composition of sums and products of continuous functions. It is continuous. And then it follows by induction that every projection is continuous, and therefore f of x is continuous. So that cleans up that proof a little bit. And that's pretty nice, I think. So let's make sure that these other corollaries also flow nicely. So the reciprocal function is continuous, so we just take this special case. And then we'll also have this other corollary saying this mapping is homeomorphism. This isn't actually super useful. We don't really need this here, this corollary. This never gets used. But I guess it's just sort of there for fun. So yeah, so we have this x is CA, f of x is this cancellation, this is constant, blah, 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 so on and so forth. Okay, so these sets, I want to say these reference exactly which sorts of sets we're talking about. Okay, show us that if we have all of these xn proportional to c and xn goes to L's conversion, then also L is proportional to c. Maybe we want to move that above this corollary. Let's see, I think actually we do. Okay. So we'll move this above this note. We'll move this above this theorem and put it right there. So yeah, so we proved this corollary. So we showed this C times A set is a closed set. And the reason this is important is because where c is non-zero, we actually have this as the set of things which can be divided by c. So the previous results actually want to say ln goes to xn goes to L is convergent, then also this thing and this thing. Okay, I think that checks out. So we're going to leave this section here. We won't edit this section anymore. We'll start in the next section, which analyzes the. Let me actually make sure that I don't need any of this. I think most of this was supposed to go in the previous two sections, and now we don't need it. So let me just let me just delete this. Stars, blah, blah, blah. Oh yeah, this is some proofs we have actually. We could probably put this in our second section actually if we wanted to. This constitutes a proof of y are a star. So we, in our preliminaries, we noted that a star is actually the pre-projection of c star. We can probably find a way to let me see. Yeah, we can probably find a way to put this. We could either put this in section 2, which is where all of this is, or we could put it in the appendix. I think we'll probably just put this in the appendix. We can do that now. We might as well, because that'll be taking care of things. So we're going to take this. Equals 1. Blah, blah. We can, yeah, all of these are redundant from what we just did. Yes, but these first parts can be moved. So we will take over down here. Oops. So we'll do a new theorem. And the theorem statement will just be a star is the set of z in A such that P1 of z is non-zero. As our proof, we will write so we want to have, so we're going to have to show, in order to show these two sets are equal. Actually, let me copy. Oh, this is fine. So in order to show that these two sets are equal, we have to show a subset relation in both directions. Actually, let me put a section star. I don't have section numbers on the appendix, I think. Hopefully that actually works out. It doesn't work out. Well, okay. I'll figure out the numbering later for the appendix. Okay, so in order to show, we want to show that every element in A star has its first index being non-zero. To prove that, we can show, let's see, we can use the z function. So show A star is subset equal to P1 inverse of C star. Oops. Note that, actually we can use, we can use the properties of the z function. So the first direction is if we have, actually let me do, instead of z's here, let me use x's, because that's sort of the convention we're using. If we have x times, let's call it y equaling 1, then z of x times y, so we have 1 equals z of 1, which is z of x times y, which is z of x times z of y, and we'll put it like that. Yeah, that might need to be undefined control sequence. I think that's maybe, oh yeah, there we go. I had a little missing white space there. That's much better. Okay, so that was there. Okay, so to show the subset relation, we use the properties of z. So if we have x star y equals 1, then 1 is z of 1 is z of x star y is z of x times z of y. And since z of x and z of y are greater than or equal to 1, then both must be equal to 1. Actually, rather, we should say z of x is 1. It's actually the important part. And thus p1 of x is non-zero. Oops. So p1 of x is non-zero, and that's our first conclusion. To show the converse direction, so we've shown the A star is subset to this other set. To show that it's also superset and therefore equal, we can use our cancellation formula. So to show the converse direction, we can use the cancellation formula. If we assumed, actually we can just use, yeah, okay, we'll state it like that. We assumed that such y for x, y equals 1 existed, then the cancellation formula would give us, and so we'll just deploy the cancellation formula here, and that's going to be up, where is it? Right here. So we're just going to copy this entire cancellation formula, and we're just going to put it down here, and then we will replace, instead of x divided by y, we actually want 1 over x. So y will be 1 over x, and we'll just replace y is, let's see, oh gosh, I'm using too many steps at once. Scroll back down so I can see this. Because we're using the same variables here, I don't want to get myself confused. So we're going to use the cancellation formula for 1 divided by y. So actually, we want to assume that this x divided by y is actually x, which is confusing. So first we'll replace all the instances here of x with 1. So this will be 1, and oh no, actually we do want 1 over x. Okay, so we'll assume, yeah, okay, we do want to have x here in this formula to be 1. And x is 1 here, and x is 1 here, and then for the y's, we're going to replace the y with x. So that'll be x, this will be x, this will be x also, this will be x, and that will be x. And this one, instead of doing 1 over y, maybe I have confused myself. Oh my gosh. It should be like this. Okay, yeah, that's right. This is correct. So this 1 over x is actually y now. So now we have only x's, and then we want to replace the 1 over x as y. Okay, so what we're doing is we're saying if there was some y such that xy equals 1, then y is equal to 1 over x. And because that's a cancellation, we can use the cancellation formula for 1 cancel x. And so this is all hypothetical. We don't actually know that xy equals 1. We don't know that such y exists. or started using transcendental reasoning. This will give us all of, if we assume, actually, yeah, we sort of skipped the premise here. So take x in P1 inverse white space. Actually, we'll just do A with P1x not 0. Then if we assume that there was some y to give us this xy equals 1, then the cancellation formula would give us this. So we know that z of x is 1, so that's sort of our premise. So we can replace all of these z of x's with 1s. Let's go and put this down here. One more. Okay, so the cancellation formula would give us this expression. So essentially all we've done, we've taken the cancellation formula for 1 over x, and we've plugged in all the terms for, we want to know what should y be if x had an inverse. What would it be? So if x does have an inverse, then it satisfies this definition. And remember, this definition is inductive, which is very useful. So what we're going to do is, we know that if our y, our multiplicative x for inverse for x existed, then it would satisfy this definition. And in order to prove that it actually does, we're going to instead assume, we're not going to assume that y is the multiplicative inverse, but we're instead going to assume that y satisfies this definition. So we're going to sort of switch up our assumptions. So conversely, for some y, so this could satisfy as a definition for y because it's inductive. If we use the above as an inductive definition for y, then we can actually just resolve this to show that the product is 1. I'm going to use a line environment here because we're going to have multiple lines. Oops, oh gosh. Golly gee, let me try that one more time. I really messed up my environment. Okay. So we can just solve this. So we'll start with this term. That doesn't belong there. That belongs there. Okay. So we start with this whole expression that we have, and we're going to solve this. So we want to multiply through by yeah. So then we can just solve the expression for this piece of k of 1. We can just solve whatever this expression is. We can just solve it for this. So this we'll start with this. We'll multiply through by our p sub 1 of x. That'll be our first step. And that lets us get rid of these left to right parentheses. So that's our first step. After that, we're going to add over this term to the other side. So we'll have this plus that. We shuffle algebra. And I also want to reverse the order of this equality. Right, so the first step is we multiply through by p1x, Then we're going to add over this sum and sort of switch the equality sign. Just sort of flip it around. And then we can just fit this right back into the summation, because this term actually is included right there. So this merges right into our summation. I'm also going to add some ampersands here so all this does align as we want it to. And hopefully yeah, we can actually remove this P1K and just do this thing, which is PKXY. Perfect. And that's the proof. So we have, if we have this this expression, so if instead of assuming that xy equals 1, we can use this as an inductive definition for y, and then we just solve for pk1. So we start with this, we multiply through by p1 of x, we put over the sum, because we're subtracting it here, so we add it on the other side. We merge this sum with this other stray term, and then this is just the definition for convolution of pkxy. And then we have equality, so we have equality on every index, so xy equals 1. And that's sort of how these proofs will work. If you can prove equality on every index, or if you can prove some property on each one of these projections, then you get the result. So we have equality, pk1 is pkxy. So we have equality, and I'll highlight that. pk1 equals pkxy on every projection. So xy equals 1. And I actually want to get a reference here. I want to reference the cancellation formula that we've solved up in our section 2. Recently I started using a new format for writing theorems and corollaries, so I actually don't know how to reference these. I think I need to give it a tag somehow. We want to reference this theorem 2.1. So let's see, actually I have this page over here open to tell me how to do that. Let's see, hopefully one of these will have a tag. They don't have tags. Oh, there we go. No, that's not what I want. Oh, there we go. As with many other numbered elements, the command /label can be used to reference theorem-like environments within the document. Okay, so I know how to do that. So to make that happen, we're going to give this theorem a label somehow. Actually, I have no idea if that's going to work how I want it to. And then we're going to see if we can tag this. And hopefully that functions the way I want it to. It doesn't. Tag null. Oh, right, of course. Tag not allowed here. Does it have to be inside? No, it doesn't. I don't know. Oh my gosh, I'm such a silly goose. It's ref, R-E-F, reference, cancellation, and hopefully that just works exactly the way I want it to. Yeah, there's the little reference. Okay, so we've given this a label. This is our cancellation formula. So down here, conversely, however, just solve blah blah blah. Okay, so we're gonna add, let's see, where is this? Down at the bottom. Yeah, so let's give this some space. Use the cancellation formula and we'll add our reference in right there for this. Okay, to show the converse direction, we use this. Oh no, the reference isn't. Oh, that's because I made it lowercase. Yeah, that's right. Okay. Yeah, so to show the converse direction, we can use the cancellation formula, and we have our reference here for that. We can take some x in A with the first fraction non-zero, and if we had y such that, there we go, this will make it a little more succinct. Okay, so let's make this italicized. Maybe I don't want to do that. Yeah, okay, so instead of assuming xy equals 1, we can just use the above as an inductive definition for some y, and then we can just solve this expression for pk1. And this all works out. And so this is this result. This proves that our A star set, our set of units, is actually this set where the first projection is non-zero. So that'll be that. So now I can also get rid of this extra stuff I have down here. All of these are not important, so you can get rid of all of this and this inverse formula. Yeah, we can actually get rid of all of this. I'm going to leave this little note here. This doesn't mean anything yet. Eventually I'll probably put this in our somewhere. In some, like, the 6th or 7th section or something, which doesn't exist yet. Okay, so now we can get on to the power series, which is what we want to do today. And before we start that, I'm going to take a 2-minute break really quick to get some water. I will be right back. Okay, and I'm back. So we're right about to start working on some results for power series. So I have a little draft preamble for this section. So we've said that a power series is a function of this form. So we have our f of x, some function, as a summation of, powers of x minus some center point times some coefficient. In this context, however, our variable x, as well as the constant x0 and the coefficient c sub n, these are all values in our space A. And the exponent, x minus x0 power n, is interpreted as repeated Dirichlet product. So this is our definition of a power series. We're going to, in this section, we're going to have a whole bunch of theorems basically studying when will functions of this form converge. And we have a really nice characterization of that. We also have the similar definition. If we have some set with no isolated points, this is kind of important, because the isolated points make it really strange. If we have a set with no isolated points, a function f, which maps this s over to a, is said to be analytic when each point x0 and s, there's a power series centered at that point which converges to the function in a non-empty neighborhood of x0. Actually, that is redundant. We can just say a neighborhood of x0. There we go. So this is our definition of analyticity. We have to define it this way because we don't actually have derivatives yet. We will, but we're starting with power series, at least this time. And this is where we're gonna start getting to use all of our nice approximation objects and relations. So in this section, what we want to do is we're going to put strong bounds on the domain of convergence for power series, and we're also going to provide a symbol metric which determines exactly when the function resulting from a power series is actually analytic. So if we define a function using a power series, we'll end up having a precise metric which tells us exactly where it's going to be analytic, so exactly where there will be some other power series. Because I'm doing this, so in my original paper I did this in a different order. I used a very creative method to prove that actually what we're going to find out is that in their domain of convergent, in the interior of the domain of their convergence, power series are analytic in their whole interior domain of convergence. And also we're going to find out that the domain of convergence of this power series, and we sort of foreshadowed this before, the domain of convergence of a power series like this is dependent entirely on whether or not it converges on its first projection, almost entirely, at least. The interior of that domain is determined by that. So we're going to set up tools to say that more precisely. So actually it's really related to the root test. So we'll define a function, and I have over in my previous draft, somewhere around here, I have a definition for this function that we want to use. Somewhere down, farther, after derivatives and integrals. There we go. So this is our functions. Yes, and we are going to put this, let's see if I can get this to go to where I want it to go. Okay, so we're just going to copy this function definition, and I'll talk about it when I do that. And also, yeah, we can say that. Okay, so we're just going to put all of this straight in. So let's see, how do we want to format this exactly? We want some description. So exactly when the function is one from the power series is analytic. Okay, so we'll do that. And at each point there is some power series to f in some neighborhood of x0. Okay. So we'll say, so C is actually going to be a sequence. So for some sequence, we'll have C sub n indexed by n in naturals, including 0. So we're going to define this function, and that's, okay, so this function that we're defining, it's a function of an entire sequence, so for some sequence. And we're actually going to label this a little bit differently, because we want to think of these as objects into themselves. So you have, don't get too worried about the fact that these are sequences of sequences. If we just think about A as sets of really weird numbers, then we don't have to think too hard about the fact that this is sort of a double sequence. But so for some sequence, we're so this is a sequence indexed by naturals, mapping into this space A. We're going to define this function so that we're using a capital phi of C, and it's defined as a supremum of limit supremums of this expression here. And actually, I need to change this a little bit. P sub k, C sub n. Here we go. That's better, because I've changed my expression recently. Okay, so what this definition is doing is essentially we're taking our C sub n sequence, this series of terms in A, we're projecting it onto some k dimension, and we're basically just applying the root test. This is essentially the root test. We're taking a limit supremum of the nth root of C sub n, except instead of just C sub n, or sorry, the nth root of the absolute value of C sub n, but instead of just C sub n, right, because we don't necessarily have a notion of nth roots of sequences. Also, that wouldn't help us in this context. Because we have sequences, we're going to take the nth root of a projection. So we can think of C sub n as a sequence with different projections, and each of those projections we're going to apply the root test. And once we have all of those root test results, we're going to take a supremum. So we're taking sort of the largest exponential growth factor of all of these projections. And that's what this capital phi is doing. Another way to think about this is that we're sort of applying the root test on each projection and taking the worst one. And what we're going to find out, so we're going to find out that this actually determines. You'll know that this is a real number. It's a possibly an extended real number. So it could be, but it'll always be non-negative. So it could be 0, could be infinite, but it'll always be some non-negative real number, because each one of these are, projection, that's a complex number, absolute value, that's a real number, and then nth root and limit supremum, those are all real things, and then supremum, that's a real thing. So this will just give us an ordinary real number. And when it's finite, so if it's infinite, then it's sort of trivial. That we'll just have to work around those cases. But when this test happens to be finite, it has these equivalent characterizations. So these are kind of sort of complicated and wacky, but each of these characterizations are sort of important. One of the characterizations, and we'll end up putting all of these in another appendix, one of these characterizations is that for every lowercase phi greater than 0, actually for each of the lowercase phi greater than 0, if we have this limit of C sub n times phi to the power of negative n, if this is 0, whenever this is 0, we're going to put this in the set, and we're going to take the infimum of all of those. So we're taking the infimum of all these phi values, which are positive. So it's the lowest positive phi, such that this limit is 0. So we're taking our Cn, and this is actually important, because our Cn, in this definition, we're not taking any projections of C sub n, but this phi is considered to be a real number. So we're taking these real numbers and we're multiplying C sub n by this real exponential that's decaying, this decaying exponential. We're saying that this is going to go to 0. So we're taking sort of the greatest lower bound of these phi's that make this happen. Another equivalent characterization, which is a little more complicated, is we're taking the infimum, again, of all phi greater than 0, such that there exists, and we have this b sub phi, so it's some b dependent on phi, and this is going to be positive with respect to our partial order procession, such that for every n, for every index of our sequence c sub n, if we take the a of c sub n, so that's the pointwise absolute value, that's going to be smaller than b sub phi times phi to the n. So this is really similar to a root test. Essentially, what we're saying is that if we apply this capital phi, then any larger value of lowercase phi, any lowercase phi larger than this capital phi, we're going to have some constant, effectively, a constant b sub phi, such that our c sub n is bounded by this constant b sub phi times this real exponential phi power n. So we're sort of finding what's the sort of the best, what's like the best comparison we can make of this sequence to a real geometric sequence. So this operation is really interesting to me, that it does that has this characterization. We'll prove all of these in Appendix B. And what we're going to assert is that this phi, this sort of root test operation, determines the convergence exactly. We're going to end up with, actually our ultimate result is going to be that if we have this phi being greater than 1, so it ends up being a real number. If it's greater than 1, then if we want to sum up all these c sub n, it won't converge. And if it's less than 1, then it will converge. And that sort of like makes sense. Like that's what you would expect. And that if all of these are decaying, so if we have our we can take some, lowercase phi to be less than 1, then this will decay geometrically on each projection. So of course we can sum up all of those on each projection, which means we can sum them up. And likewise, if it's a greater than 1, then there's some index where it doesn't sort of reach that qualification. If it's equal to 1, then we'll just have some inconclusive result. We won't know whether or not it does or doesn't work. What's important about this is actually what we want to know is that if we multiply two sequences together, so actually something that we want to prove, and I'll state it here, is that if we have phi of some sequence c sub n times, and we'll use our pointwise Dirichlet product, times some other sequence, actually I'll just call it b sub n, because why not, b sub n times c sub n, these are indexed by natural numbers. This is going to be less than or equal to, what I want to say is this will be less than or equal to the maximum, no, it's not the maximum, it's the, I think it's the product, right? So phi of our c and times phi of b. I'm going to put these in reverse order because that's what I've done it as. And actually we can just use a and b. There's not really any reason to use c here. Let me just change all these around. Also, I want to change this one. Okay. Do that, and we'll also do this. Okay, so the characterization that we're using is good. Okay, yeah. So what we want to try to prove, one of our results is we're going to prove that if we use Dirichlet product to product two sequences together, if less than or equal to sort of the product of their phi values independently. This is really similar to just real sequences. If you have two sequences that are sort of geometric sequences of real or complex things, if you multiply those sequences together pointwise, then that's the same as sort of multiplying their base together. That's sort of like the essential law of exponentials. The reason that we get this less than or equal to, it's actually not because of this convolution. It's actually because we're taking, in calculating this phi value, we're taking a limit supremum. So we don't necessarily know that all of the terms are represented very well by an exponential. it might be the case that only some of the terms are well represented by an exponential. And when we multiply these together, it's possible that it end up actually being smaller than the product of those bases. If they were pure exponentials, this would be inequality. But we're just going to prove this inequality for now, and we'll use this. So we want to write a theorem for this. So we'll start, and we're going to end up putting this somewhere, but begin theorem, and we want to put this statement in there, and we'll put some also dialogue. So for any sequences A, B, and A with indices naturals with 0, we have this. We have this inequality, and we're going to prove this inequality here. I hope you guys can't hear. There's like a lawnmower outside. It's actually really loud. I hope that's not too bothersome. Okay, so we're going to set up this proof. And the way that we're going to prove this, so in order to prove less than or equal to, I think what we want to do is we want to use one of these other characterizations. So this limit supremum characterization is not super useful all the time. It's really easy to calculate this characterization, but it's not useful. It's not very useful on its own. So actually what we want to do is probably use the second or third characterization. Probably the third one, I think. So we're going to use this third characterization. So get rid of that extraneous line. So using the third characterization of capital phi, take any, we'll do phi sub 1 and phi sub 2, and we'll do phi sub 1 is going to be greater than capital phi of A, and phi sub 2 will be greater than capital phi of the B sequence, so the second sequence. So we'll take some of these small lowercase phi's greater than these respective capital phi values, and then we can find, actually I'll actually change this up a little bit as well. Instead of doing a B here for bound, I'll actually just do capital A so that it agrees with our sort of convention of our variable convention means. So the A sequence would correspond to A, and this we would have a B sequence corresponding to B. So take any of these phi values and find, we'll have A sub phi 1 prec equals 0. Actually this is going to be the other way. And we'll also have B such that we're just deploying our third characterization, that's this one. So we're going to take our two sequences, and for each sequence we're going to find some of these coefficients. Oh, okay, that's good. So we're going to find these constants, the boundary sequence. That's going to make this really easy, actually, because the only sort of moving part with respect to n, once we use this characterization, the only moving part is just this real exponential, and all this sort of the sequence components to it just sort of don't matter anymore, which is going to be really useful. So using the third characterization of phi, we take any phi 1 greater than capital phi of A and phi 2 greater than capital phi of B. Then we're going to find our coefficients, and we're going to have A sub n smaller than A sub phi sub 1 times phi sub 1 to the n. That's our first one. And we're also going to have the second one. So our B sub n will be bounded by capital B phi 2 phi 2 power n. And we can probably change, instead of doing phi 1 and phi 2, we can just use like phi and var phi. But it's really symmetrical this way, so I think maybe it's okay. So we're using this third characterization. So for each of phi 1 and phi 2, if they're greater than each one of these respectively, we're going to find then our coefficients, such that we have these. Let me do an and here, so that we have some white space between those. It makes it a little more readable. Yeah, so we have this a sub n is bounded by capital A and phi 1 power n, and b sub n is bounded by b and phi 2 power n. And then we can just multiply these together. Actually, let me do a think. So both of these are bounded by 0. So actually what I want to use is the fact that if we have x preceding y and 0 preceding z, then x z is preceding y z. That's sort of what I want to use, this fact here. And this does actually work, even though these are convolutions. And we can get these from our properties, although I haven't stated that this is true, and it's not trivial, which means we'll have to prove it somewhere. So we're going to put it in an appendix, like we do with everything, because we're very lazy. And we don't want to clutter up sort of everything with these little tools and techniques. So up here, right around here, I think, we're going to put this statement. So we'll have 0 is smaller than z and x is smaller than y, and that'll imply xz is smaller than yz. And then we'll also put an ampersand here, and we want to make sure to have our new lines correct. Okay, so this is the statement that we wanna have here. So we have this procession. That didn't align correctly. That's because I put the ampersand after the imply symbol. Okay, there we go. So we're gonna actually put this in the appendix. And oops. And we're just gonna go straight to the bottom. So last time in our appendix, we proved this A star, that's fine. We proved this relation. Actually, this is the one that makes it work. And the proof is actually super simple given this. So we're just going to add a new theorem and a new proof with it. So the theorem statement is for any, we'll have x, y, z in a real, so for real sequences, if we have this and this condition, then we have this other one. And we've put this right here, yes. So if we have z is positive with, where'd it go? Right here. If you have x, y, and z, which are real sequences, real elements, and we have 0 is preceding z, and we want an and here, so that's, again, we want like some conjunctions, and x is preceding y, then xz is preceding yz. So how are we going to prove that? The way we're going to prove that is sort of in reverse. So we want to end up having xz preceding yz. So another way that we could do that is, because we know that we should have, so we'll actually make that as a note. So actually, that's not important. So we know that xz and yz are both going to be real. yeah, we know that xz and yz are both going to be real. And we also know that our procession operator sort of, our relation, works well with addition. So if we want to do sort of what happens next is we can subtract xz from both sides. So sort of the next step along, and we're working, let me scroll down, so this is at the top. So we're working on this one. So we want to end up here. What we can do is we can subtract xz from both sides, and so we'll end up with this. We can just factor the right side, because that doesn't change the value. So we'll factor out the z, and it'll end up like this. And then what we want to do is we know that our y is sort of greater than x. That means that y minus x is greater than 0. But because that's true, then y minus x is exactly the same as a of y minus x. And likewise, because we've asserted z is positive or not negative, then also we can apply a to z without changing the value. And I messed up the new line there. So we can actually apply a to both of these without changing the value at all, because both of these are positive, y minus x and z. But if we just go up to here, up to this previous result, we know sort of by just this result that this product over here, this is larger than you know, a of the product is less than the product of a's. So actually, just sort of without any other work, we know that at the very least, if we have a, we'll do y minus x times z. I've added too many white spaces. A line environment doesn't like white spaces. Okay, so we know that this last line is just true. It's true based on the previous theorem, this 4.1, which proves this inequality here, this submultiplicativity of the a function. So this is true, and then all we need to do is to get from here up to here. But right here we just have this a of something, whatever that is, and we have non-negativity, actually. So we end up with this, and so this is sort of what we want. So all we have to do is take this and go in reverse now. So we'll just take each of these statements and we'll put them in reverse order. So we'll start with this statement. Let me fix that up again. Yeah, so we'll start with that statement, continue with this statement, and then this one, and then this one, and that one. So we've just reversed the order of the proof, and hopefully this will all follow logically. And also, because this is in an align environment, I can put some alignments here. Not quite like that. Almost. There we go. Okay, so the first one we're going to state, we have to justify this. So this one follows from this. And that gives us, because of our sort of, we have this conjunction of inequalities, we can combine these for just this thing being less than or equal to this other thing. Then from there, we know these are positive, so this a function just goes away in both cases. We expand it out through the distributive law, and then we just add xz to both sides, and that gives us our result. So we can just add a little bit of text here. So because, yeah, so we can use, this follows from the previous result, and I'll give this previous result a label. We'll call this submultiplicative. So this follows from reference submultiplicative, and the So this follows from the submultiplicative of this result, and also the linear properties of our inequality relation, our partial order. So we actually want as well as non-negativity. Okay, so this should hold. So we have this follows from non-negativity of A as well as 1.4, and we also want to do and of this procession with addition. Oh gosh. There we go. I don't really like how there's just this one word on this other line. We'll figure it out. But yeah, so this should hold. So non-negativity of A as well as 1.4. I guess I can just sort of suppress this. So we have this, and then we have, so we go down here. Maybe we can make this a little more explicit, so we can this is okay. It's not that big of a deal. We'll just leave this as is. So this gives us this property. So we do actually have this. If we have two positive, or actually not necessarily positive things, but if we just have two things which are real and related to each other, and some positive thing, then we get this relation here. So we can scroll back up to power series, which is where we're working on. So now we can use that property, now that we've proven it. So we have our coefficients here. Now we can just have we can actually just multiply them both. So this then gives, I'll do, oops, another inline environment. So we're going to start out with, actually, yeah, maybe we should note this. Okay, so we'll start out with, we have this first inequality, and then we just multiply both of these with our b sub n, a sub n star b sub n, and also on the right side we'll have this thing times b sub n, but we also have too many white spaces. So we have our first inequality, we just multiply both sides by b sub n. This is valid because our a of b sub n is non-negative. And then we also want to turn this expression here into this other term. So we have the first one times a of b sub n gives us this first expression. But if we instead take this second term, the second inequality, and instead of multiplying it by a sub n, we're going to multiply it by a of phi 1, capital A of phi 1 times phi sub 1 power n, because that's also going to be positive. So we have this star and then times that. And this will give us our total inequality. So a of this thing is preceding this final product, which we can rearrange. So we can put our a of phi 1 up to the front, and then we can factor out these phi 1 times phi 2. So phi 1 times phi 2 and power n. Yeah, so we have third characterization of phi, blah, blah, blah. Find these a, b, so we make these bounds, multiply the first one by b, which gives us this, multiply the second one by a phi 1, and note that this term here is the same as this. Multiply the second one by a phi 1 to get this, and then we just sort of combine these. And we can also, if we want, we could just merge these down like this, and that would be okay. So we have this sort of combined inequality. So a of an times a of bn is preceding this thing, which is preceding this other thing, and this is just equal to this rearrangement that we did. And we can also go one step further. On this far left side, we can again break this down to just a of a sub n times b sub n. And that actually gives us the full inequality that we want. All we have to do is, on this far right side, we can just factor out these terms. There we go. So a of an times bn is now, through all of these different inequalities, bounded by b times a, or I guess I should do in reverse order, so that'll be a little more easy to read. A times b times this exponential phi 1 times phi 2 power n. And then, so again, by the third characterization, of our capital phi function. So because we have some term which is bounded for every n, is bounded by this some constant times this geometric thing, while our third characterization of our capital phi function is just the infimum of these values where there exists some coefficient, which makes this true. And right here, so we have our a times b series as bounded by some constant times phi 1 times phi 2 to the n. So this shows that capital phi of the series a sub n times b sub n indexed by n in the non-negative integers is less than or equal to phi 1 times phi 2. Let me do that a little more like that. Okay, so now we have this inequality. So we've shown that for each phi 1 and each phi 2, where phi 1 is greater than capital phi of a and phi 2 is greater than capital phi of b, we have this inequality now. So now we can just take the infimum across all phi 1 and phi 2 by taking all phi 1 and phi 2, we get the result. So just adjusting the wording. Okay. So since this is true for every n, by the third characterization of phi, we have, and I don't like this is, since this is true for n, then let me actually rearrange this like that. Just rearrange those statements. Okay, so by the third characterization of phi, we have this thing, and then by taking the infimum across all phi 1 and phi 2, we get the result, and we'll just restate the result, which is that phi of, and let me just copy these because I don't want to type this whole thing again. Phi of this whole thing, and actually I can just copy the entire statement as is. Just like that. And let's also add a little bit of space here. I tend to add some spaces before my theorems. It gives it, especially like this, gives it a little more readability. So we have our theorem for each A and B sequences. We have this inequality relation. And so this lets us use this inequality whenever we want. So this is going to be super useful for us. So if we know some phi of some series, and we sort of convolute them together, and we use our Dirichlet product, and then we have this inequality bound. And this is actually exactly the same as real numbers, which is great. What we don't know yet, what we don't have a theorem for yet, is what is going to be the growth of these repeated exponents. So we know about Cn, and if we knew the growth of these coefficients, that would actually give us a pretty tight bound on the convergence. So all we need to know is what is the growth of these repeated powers, and that's going to be the next result. So the next result is going to be, and we can add some more exposition in between later after we write the theorem. So the next result is going to be another theorem with a proof, and the theorem is that we'll have for each x in A, we have capital Phi, and our series is x power n, indexed by n in naturals. And actually what we want, what we're going to show, is that this phi is precisely equal to, we'll end up with, let me think for a minute, it's P1 of x, absolute value of P1 of x, every time, which is excellent, I think. Let me make sure that's right. Yes, okay, that's correct. So, so normally if we're in real numbers, if x were a real number or a complex number, for example, this capital Phi would just be the root test, and this xn series is just repeated powers. And since this capital Phi is just doing the root test, and we just have a simple geometric, on the real numbers, this would just result to absolute value of x. But we're not on the real numbers, but it turns out we have an equivalently simple characterization, which is that we're going to see that when we apply this root test on these xn's, we actually get that the absolute value, that it's the absolute value of just x on the first index. And so this is sort of, I was mentioning how we're going to find out that this first projection is really important. If once this ends up being true, we actually prove quite a lot about the convergence of our power series. We've proven that if we just know sort of the convergence of the first projection, that'll tell us the convergence overall. So that's what we're building up to. And that is exactly like the root test. We have a radius convergence, which is a real number, and only the first index, only the first projection matters. So in order to prove this, so I actually already have a proof sketch of this laid out. And this proof is not easy, so we're going to reference that proof sketch. So this is the proof sketch. It uses sort of our old notation. So we're going to have to sort of import this, but it might be a little easier. It relies on an induction, but gosh, this is quite a lengthy proof. So we'll have to break this down into pieces and sort of work on that. So let's see. So the way that this proof goes, and don't try to read too much into it just yet, we're going to rewrite this whole thing. But the way that this proof goes is we construct an inductive representation of some repeated convolutions. And that's going to give us this particular representation. And what we want to do is to use this representation to show this relation. That's going to be a little hard. Let me see if I can make that a little simpler. I know what we can do. We can actually just recycle this capital Phi function a little bit, I think. Let's see. How do we have this? So there's a whole bunch going on, for sure. Yeah, so what we're going to end up doing, so what we have here is we have in our old paper, in our old draft, we have xn projected onto the k axis, and we have it equaling this summation. And the summation that this is so it's some finite sum of some x on these lower indices, so that indices lower than k, the lower projections. And we have this other summation, and this is actually sort of important. Which is that this lower summation is running through different powers of x. This is actually very similar to the binomial theorem. That's fun. So we want to try to, let's see. That's phi sub j. So we have each of these tending 0. Yeah, so we want to use sort of an inductive premise. And we end up showing phi greater than x1, j magnifies 5m, sub phi sub j, these things. And eventually we're going to end up like this. Oh, I see. That's interesting. Okay, so the way that we've proven this last time is we've just sort of gone ahead and assumed a growth on each index. So for each of these, m sub phi sub j, which may be finite, must be finite, such that this supremum across these indices and a natural 1d xn phi sub n going to 0. Okay, so yeah, so take any phi greater than norm x1. You see that? Oh, yes. Okay. Yes, this is actually what we want to do. Okay. So let's try. We definitely are going to need this inductive formula. So this inductive formula lets us express our xn power on the k index. This lets us express this in terms of lower indices, just all lower indices, finite sums of lower indices. And then also, somewhere in here we should have the x, so d less than k, x1, and this is the only outlier, I think, which is that sometimes this will be k, this one, this index, this will be k when x is, when d is 1, so we'll end up with d is 1, let's give us d is 1, and then we'll have some 1 powers. We may have done, okay, well let's just work out this sort of inductive definition. So that's what we want to start with. So we're going to sort of piece apart this. So we want to go, the way we've constructed this formula, we take x power n on some projection, we separate this into x times x n minus 1, and we give it this summation. So, so take some n greater than 1, and it could be possibly much greater than, and consider the following decomposition. So we're going to take so we have x power of n and we're going to, we should put that there. We're going to project this onto k, and this is actually going to be equal to a piece of k. We have x power n minus 1 times x. And some, actually we want n greater than 0. I think. So we have our projection, our power, we have our multiplication, and then we're going to expand this as a sum across divisors because we have a convolution here. So AB equals k. Our first one will be PA of x power n minus 1, and the next one will be PB of x. So this is the first step, so we expand our convolution. Our next step, what do we do next? So we expand this out, and then we also, so we expand this out, we pull out this term where it's n minus 1 power k. So we're going to pull out that. So this will be, so we have the same summation, and we want to restrict a strictly less than k, and we pull out the term where a is k. So we pulled out this term here, and in this case a is k, so pk and p1. Okay, and this is going to actually let us, yes, so now I can see how this is going to work out. So we pull out this term, and then we do an induction through n. So we'll have this equals that, and this is going to be, we'll do some better alignment here. Okay, not bad. Now we can do an induction, so we can do, yeah. Through n, we get, so basically what we're going to do is we're actually going to just take this expression. So we have this term as equaling this thing. So we have, so what this first part is showing is we have this k projection of x power n. We can split this up into a product, and that gives us this thing with this other stuff. But what we'll notice here is that we have this other x power n minus 1 instead of x power n. So actually, by reducing this power, we've multiplied by this x and then added this other term. So we can sort of break this down in an induction by just summing up all of these terms and multiplying through by this power of x. But in order to do that, we're going to want to write p sub 1 x power 0, because that'll make that a little more clear. So each time we lower this index, this power by 1, we're going to get an additional factor of p1, and we're going to add this sum with however many factors of p1 of x. So when we perform our induction, we'll end up getting, so our first term is this term, and we'll do this a little explicitly at first, so that we can really see how this induction is working out. For the second term, so we have that first summation, and we're going to essentially do the exact same thing, but we're going to have p1x, so we have whatever this whole expression is. We're going to copy this, actually, and instead of n, we're going to replace n with n minus 1. So we're going to decrease all of these by 1. And we're going to take this entire expression and put it in place of this pk xn minus 1. And this is going to look kind of ugly at first. And we'll work it out. We'll expand it, and we'll end up with our inductive sort of definition for this. This is very long. Yeah, so I want to do, actually, we can shorten that up if we would like. We can shorten this up here, and here, and also here. And hopefully that won't overextend our writing space. Yeah, so we have this projection equaling this thing. We just plug this exact formula in, but for the lesser index, x power n minus 1. We end up with this. And then we're going to expand that out. So our p1 of x will end up being squared here. We'll get an extra factor here. And that concludes that with a distribution. So we get this, and then that. And we can also do this here if we would like, because that helps us see it a little better. And I actually don't know how to do vertical dots in LaTeX, but eventually we'll end up with whatever this term is. We'll do a sum, and we'll do, let's say I equals 1 up to sum k. We don't know what that is yet. Actually, we don't want to use k again. We'll use an m, and we'll have this power. Actually, let's start with 0. No, we'll start with 1. We'll do this power. The exponent will be I minus 1. The thing we're subtracting from n will be I. I think that should give us, whoops, that's not right at all. That's better. Okay, yeah. So we have this summation. I think this should be, if we just have an m here, we still want this little leading term out here. This thing plus this other thing. And the exponents that we have is, so the way that this is aligned is, so as we're summing through m, this exponent here is going to be at most 1 less than m. And right here, when we have this repeating sum, we have 0, and then we have 1. And up here, we have this exponent being 1 greater than this greatest p1 exponent. So this should be m. So we can replace this 2 with m, and replace this 2 with m. And that will give us this right here. And this works for whichever m we want. So we can actually bring this all the way down to n, m equals n, and this will be 0, this m will be n, and this m will be n here. And that's sort of our inductive formula, and then we can just simplify this a little bit. So we know that x power 0 is just 1. So this pk x power 0, this will just be 1, yes. So that's just pk1. We might need to do the first index as a special case. Oh, it split it onto another line. That's okay. We can also lower this down to just 1. We don't need to duplicate that line. Okay, there we go. So by performing an induction through k, we get this summation. So this is our pkxn, and we end up with pk1, p1 x power n, and then we have these extra terms here. And what we want to do is now we're actually just going to swap around these summations. So here we have sum of ab equals k. We can actually just pull this to the front of this little summation here. Then we have this sum of I equals 1 to n as being second. And any term that doesn't have these indices can just sort of be ignored. Let's get rid of that. We also don't want to reduplicate this, so I'm just going to get rid of this. And we'll also get rid of that. Okay, so do our piece of k, x per n, we'll have it going this thing. Okay, so okay. Vertical dots, v dots. Yeah, that would be useful if I hadn't just erased that. I will remember that in the future, though. Okay, so we have this summation. So we've extracted. So what we're saying is we've extracted this pkxn minus 1, the same as what we started with, but with the exponent 1 smaller. So we started with pkxn. We ended up with pkxn minus 1. And this lets us perform our induction, and we just sort of skip through the inductive steps to get to the end. And we end up with this whole weird summation thing. And then we've just rearranged these summations. I think that's... let me think. How did I do it originally? I think I might have done, yeah. Okay, so it's very similar to how I did it in the previous one. I had m equals initialized at 0 and then ended at n minus 1. And this time we're starting at 1 and ending at n. That's fine though. So what we're going to do now is, now that we have this inductive formula, what we're going to do is we're going to pull another induction. So we have our, I believe, yeah, so because we have sort of brought this exponent all the way down, so we brought it all the way down through our induction, this pk is now just 1. So there's no x like in this expression anymore, in this part of the expression. This is really important because all of these projections are less than k, except for this one here. I think I might have solved that a little further. So yeah, we get this thing. 1 and d wasn't. Is that true? Okay, yeah. Yeah. Okay, yeah, okay. So I think this is fine. Because there's no exponent on this PB, we can sort of treat this as if it itself is a constant. So what we're going to do is we're going to form an inductive approximation. We know that if we do an inductive approximation on the indices k, if we can form some bounding approximation on all of these terms, actually, no, yeah, that's fine. If we can form some bounding approximation on all of these p sub a, so remember a is less than k here, if we can form some bounding approximation on all these lower terms, for all exponents, then we can sort of plug that in right here and sort of simplify this whole thing out. And hopefully that's going to get us something a lot simpler. So we're going to just do that. So now we will this one's going to be a little bit more explicit of an induction. So take the premise. So we were going to take a premise that we have already formed some approximation on these terms. And what we want to do is, I want to make sure I get this approximation right. So our premise is going to be, okay, so take lowercase phi greater than this p1 of x. And then take the premise that this implies this less than that, and that's as I take it into infinity, this will be that. So inductively across k, yeah, take the premise that that for each phi greater than p1 of x, this should be absolute value of p1x. I think that's because, no, that's fine. Yes, for each phi greater than the absolute value of p1x, we want to take the premise that every j less than k has for each of these phi's this limit approximation. So x power n on this lower index times phi power minus n tending to 0. So what we're going to do, we'll just take the premise that for each, instead of j, we have, I believe, a, so a less than k, each index a less than k, and we have for all phi greater than absolute value of p1 of x, all phi greater than blah, we have, okay, so we have x power n projected onto the a axis and multiplying by phi power n goes to 0. So that's sort of our inductive premise, which is that we're just going to take the premise that these limits, so if we take, I think we need phi power negative n, actually. That is correct, yes. So we're taking our inductive premise that for each of these lesser indices, a less than k, so for each of these ones, that this limit, this a of x power n times phi minus n, tends to 0. So that's sort of our premise. And then what we're going to prove, we're going to use this statement, so because of this, we can find some bounding coefficient. So then, also this is true, so in the base case, and we like these vacuously true base cases because they're very easy. Means we don't have to do any extra work. So we'll take this premise that these things limit to 0, which is vacuously true when k is 1. And again, that's because there's no positive integers a less than k, a less than 1. From this, we can find, we'll do m sub, what do we want to do? Over here we found our bounds. Oh yeah, okay. So we'll find m sub phi, which is a positive real number, such that we have piece of A, x power n times phi power negative n, as being strictly less than m sub phi for every n and A. So we just want one m sub phi. So m is going to be our bounding constant. So this projection, and this should be absolute value of that. Yeah, so from this we can find, so if all of these limit to 0, and there's only finitely many a's, less than k, we can find some m sub phi greater than 0, such that these projections, if you take their absolute value and multiply them by phi power negative n, that's going to be strictly less than m. So that works out because we have, our limit is in terms of n. There's countably many values of n, and it limits to 0. So of course, definition of limit, we get this m sub phi. For each a, we would get some upper bound. And then in order to get this m sub phi for all of them, we would just take the supremum. So that's sort of straightforward real analysis on bounding sequences and such. So we have this m sub phi, and now with this m sub phi, we're just going to sort of put this right into here. So what we want is array phi, blah, blah, blah. So eventually in our original proof, we find our m values, and then so we just apply triangle inequality, it seems. Although, oh, right. I think we take k greater than 1. That's how we get rid of this other term. I think that doesn't matter for us, though. Because we can still just work with this thing. Yeah. So the other way to work this out, and this is sort of what I wanted to do to simplify this. So eventually, what we're going to do is we're going to take this approximation, we're going to plug it into this point here, and then as we sum across these things, so we'll have this thing will be sort of approximated by some power of phi. And also, some other expression. Yeah, so this term here will be approximated by some power of phi, which we can bound actually this also with some power of phi, because we know phi is greater than this p1 of x, and this is p1 of x right here, so we could bound this with phi if we wanted. And then this summation is just, this is just a sum, this is geometric series, a finite geometric series in n. And we have a closed form representation for that. That'll give us some other geometric thing. And eventually, we'll end up, so we have this finite summation of some geometric things, and then this thing is also some other geometric thing. Instead of doing all this work, what we can do is we can use this, so we can add a second result for our capital phi series, and we can actually do, so in addition to the fact that this is sort of sub-multiplicative, we can do a second result to show that it's sub-additive. And what that is going to give us is right here, instead of thinking of these as all these projections, we can think of these themselves as sequences. And we can think of applying, instead of applying phi to the whole sequence, where we take this supremum of all these projections, we can just apply phi to the projection itself, which is, again, it'll just be the root test. So we can apply phi to each of these terms. We can show that if we have some, oh, maybe that won't work. Maybe it will. So we have each A will have some bound, and we'll have this, we'll have to do a little more extra work though if we do it that way. We can still do that though. So what I want to show is that when we take this summation, if we know that we have something which has a certain phi value, and we have some other thing which is less than or has a certain phi value, when we multiply these two together and sum them up to n, we want to sort of have a shortcut to say that this also has a phi value less than that. And that'll let us skip this all of this nonsense. And it'll give us a more general result. So we'll do that real quick. So what we can do is we'll copy sort of the format of this theorem right here, and we'll get another result here. And so instead what we want is for sequence A and B, we have the phi, instead of their product, we want their sum, and it's less than or equal to actually the maximum of the phi values. And this one should also be pretty quick. Instead of using the third characterization, we can use the second characterization. So actually this hardly needs a proof. So if we just from this second characterization, the phi value is the infimum of these lowercase phi, where this limit, where you multiply this exponential, tends to 0. But of course, phi greater than this max. When we do this all out, and we work out we get the limit of n to infinity. Our second characterization has, where'd it go? That's right here at the top. This limit of phi power negative n, so we have a sub n times phi power minus n, and we can also do a plus limit of n to infinity. We can have b sub n and phi power negative n, and this will be 0. And on the left side, we can do this. Instead of an and then bn, we have an plus bn, phi power negative n, and we just sort of separate all these out in the sense of being 0. So we have this thing here, put that in like that, so equal to phi. Probably we'll turn all of these into lemmas, I think. So our first one is we have, if we multiply them pointwise, then it's less than or equal to the product. If we add them, it's less than or equal to the maximum of the phi values. And the last one we need is that if we sum up, sort of doing this sort of reversed sum like this, if we do this reverse sum, then we want to say that this will be also having the same phi value. If we sum them, do this reverse sum up to n. So we'll just say that. And here we have, let's see, these indices sum up to n minus 1, actually. But we can think of these as summing up to n if we want for simplicity. And we'll do that in our next one. And so our next result we want is, give us some space. Oh, I don't have, oh, that's because this isn't, I just messed it up. Let me fix that. I actually want it right in here. Got a little mixed up. Okay, so the theorem statement that we're going to have here for this last result, if we have these sequences, then we have, actually we want to say if they have equivalent. Oh yeah, okay. So for right here, we're gonna do, let's do some preemptive fixing of these brackets. And we're gonna replace this series with a summation. We'll do a sum I equals 0 up to n, and we'll do a sub I times b sub n minus I. And this has actually the exact same inequality. Okay, so this is saying for any sequences a, b, and a, we have this phi, oh gosh, where'd it go? What do you mean? Oh, here it is. I messed it up again. This has to go... Oh gosh, what did I do? I really messed it up, actually. Okay, oh, whoops. Okay, I see what I did. Let me move this up there, and we'll also take this proof, and that should belong there. Okay, fixed it. So we have the product inequality, we have the sum inequality, and we're also going to have this. So right here, what we actually have is, and we can put this down actually, down like this. Yeah, so when we do these sort of repeated sums, and we do sort of, this is actually in itself sort of a convolution. This will be less than or equal to the max of these 5 values. And the way that we'll prove that is actually exactly how we were going to prove it down here. And so we'll say take any phi which is greater than the maximum of these two values. And what we're going to do is we're going to sort of show that these rising and falling powers sort of cancel out. And the way to do that, so take any phi here, then find, so we'll find a sub phi and b sub phi with a of a sub n bounded by a sub phi times phi power n, and a b sub n bounded by b sub phi also times phi power n. And then we're just going to sort of solve this. Yes, okay. Okay, so we want to say by the triangle inequality for our pointwise absolute value function a, we have the following. So we'll set up this summation. We have, so we'll start with this summation here. Oops. Oh, that's not where that belongs. There we go. So we start out with the summation, and we can do a left parenthesis, right parenthesis, and this will be bounded by this sum of a's. We have this and that, and then this will also be bounded. We can just do each one of these. Oops. Just like that. So, okay, so we apply a to this summation. That gives us by the triangle inequality, and then we have submultiplicativity. And then we can deploy our approximations for our upper bounds. So we have our a sub I is bounded by capital A sub phi times phi to the power of I, and this b is bounded by we have bn minus 1, so this will be b sub phi and then phi power n minus I, and we can do that replacement there. So this is our first sort of sets of approximations, and then we can just factor all of these terms out, right? So these phi's combine, these phi's n minus I, and then I, that's just phi power n. B sub I factors out, A sub phi factors out, and then we're just left with actually this much more simple expression. Whoops. And I'm going to have to sort of take some more vertical space on these, but we end up with this, and this is just going to be finally a sub phi, b sub phi, phi power n, and we also just have n in the front if we want. And we can remove this intermediary step here, right like that, because that is redundant. Okay, so we just sort of form all these approximations. So we start over here on the left, and we sort of move through these different approximations, and then we just factor all of these out, and it just ends up being, actually this should be not n, but n plus 1, because we have I going from 0 to n. So we end up with this, and now what we can do, so when we do, so normally what we want to do is we want to show that when we take this phi, and we do this sort of multiply by phi power negative n, that this will limit to 0. That's not going to happen with this approximation because we have this n plus 1 here, but instead we can sort of do sort of another workaround, which is now take any, so we'll do bar phi greater than phi, then we have bar phi over phi being strictly greater than 1, so we have this thing, so we have, actually we'll start out, yeah, okay, this is fine. So we have this summation, if we multiply this by bar phi power negative n, I accidentally have too many stuff here, is equal to, we'll have a sub phi, b sub phi, and then we have n plus 1 times we have y over var phi power n. Actually, we want to do like this, same statement, but different orientation. Oops. Okay, so instead of showing that when we multiply by this phi power negative n that'll tend to 0, we'll just use any var phi greater than that, and we'll show that that tends to 0. So this is that. So we get this when we multiply by this var phi, and actually we can take this whole left side, var phi power negative n times the summation, and this is proceeding or equal to this whole expression, which goes to 0. Yeah, and that's actually all we need. So we can do limit as n goes to infinity of this thing, proceeding or equal to this limit of this thing, which is just equal to the same limit, but we have this expression there, and then we have a phi and b phi, and this limit is now 0. Nice, okay. Yeah, so we've used these approximations. We've shown that when we do these summations, we'll get all of these bounds. So this is the triangle inequality, this is submultiplicativity, this is our approximations that we assumed by our phi values. And then this is just reduces to n plus 1 times this. And then we take this this original term now. So now we have this original term bounded by this. We'll take that and multiply it by var phi power negative n, where var phi is greater than phi. This is bounded by, so we have our original, this approximation now, multiplied by phi power negative n. We can pull that in to have phi over var phi power n. This is less than n. When we factor out these constants, so these are constant by n, when we factor these out of the limit, we just get this limit. So it's some linear term times something, which is decaying geometrically. And that's 0. So this is just sort of a standard real analysis limit. Actually, let's do a little more explicit. So then capital phi, and actually want to use, I don't want to type this one again, so it's phi of the summation here. Okay, hopefully that is a little clear. So we can add some more white space here and space things out a little better. But since we've shown that this limit goes to 0, we can actually, so by the so by the second characterization, so we have this limit times this var phi power negative n tending to 0. That's just the second characterization of our capital phi function. That's this one. This limit of phi power negative n tends to 0. So by that characterization, we get that this phi of these summations, which is what we're analyzing, is less than or equal to var phi. We only required that var phi was greater than this regular phi. So if we take a var phi to its infimum, this gives us that this term here is less than or equal to phi. And then taking phi to its infimum, we only restricted phi is greater than this maximum. That'll give us the conclusion. and that's the proof. So that's very nice. So it's sort of the same techniques as that. We just find some large enough phi to sort of make these go to 0, and we do all these approximations. This is all pretty nice and exciting. So this gives us this now is less than or equal to this maximum. So actually, in the case that these are equal, it sort of gives us a perfect bound. So this is going to make this theorem a lot easier. So once we end up with this, decomposition, we perform this induction to get this expression, and now we can perform an induction on k. So take the premise that for each index a less than k, we have, and we're just going to use the var phi function directly, so var phi of the series, we'll actually just do p sub a of x sub n, and, or sorry, x power n. This is n in naturals with 0. We'll say this is less than or equal to this thing here, this bound, the absolute value of p1 of x. So take the premise that for each index a less than k, we have this inequality. Then by our lemma, which is not labeled a lemma right now, we get the var phi of this thing. So phi of this series across and in less than or equal to also this. Okay, this one. Okay. Our lemma, we got, yeah, so by our lemma we get this phi of this summation as being, let's see. Okay, yeah, okay, let me do, yeah, so first, so that trivially we have phi of the series p sub 1 of, actually, p sub 1 of x, and then to the power of n, where again n is in naturals with 0. This thing is actually equal to norm p sub 1 of x. The inductive premise. Okay, so we've got our phi of our p1 terms, this exponent. Gotta rearrange all these pieces. Yeah, okay, so by our inductive premise, each index, take the inductive premise that for each index a less than k, we have this phi being less than absolute value p1. This is vacuously true when k equals 1. We notice that this is just a standard series of exponentials, so it's, if we apply phi, that's the root test, we just get norm phi of whatever this thing is, or norm of whatever this thing is, which is p1x. Then by our lemma, which is going to be actually this term here, this summations, we get that this phi of this whole summation, that's this whole thing right here, this is less than or equal to norm p1. And then yeah, so let's put these on different lines. So we have, first is this sort of rising falling sum, and the next one is this total expression, which is, we'll have this thing. Let's put some okay, that's a little better. So we have this, and then we have this other term, so this would be phi of this other thing. Q1x power n, p k1. Okay, okay. Okay, so if calculus is true when k equals 1. So by noticing that this is this, and phi of, we have series, oh, p1k is just a constant. Yeah, okay. Okay, so reduction through k, take the premise that we have this phi relation, that these phi's of these lower projections for a less than k of these powers of x are less than or equal to p1x. This is vacuously true when k equals 1, because there's no a less than k. Then we notice that this, if we just have this standard geometric p1 of x power n on the outside, this is just the absolute value of p1 of x, because it's just a standard geometric. Then from our lemma and subadditivity, so from our lemma we get this expression here, that's this one. And then from subadditivity, this is a finite sum with just some constants here. So that gives us this, and then actually, really, that gives us the whole thing. So from our lemma, we get this, and from subadditivity of phi, we have the conclusion, which is actually, we don't have the conclusion. We almost have the conclusion. We only have this one is just this thing, and instead of being equal, we've shown that it's less than or equal to that. So phi, this whole expression, this thing is just equal to phi of this whole thing, which will be less than or equal to that. So you want, let's see, get some of these. that, and also this. Oops. So phi over x power n is equal to phi of this thing. Actually, we want phi of the projection p sub k x power n as being less than or equal to that. And since this is true for every projection, then we get the upper bound in general. Not x power n, just that. And there we go. So that's the first inequality. So we've actually asserted equality here. The equality the other direction is actually really easy. But we have so we start out with this decomposition. So we say we take our projection, split it up into this convolution and this product, expand it out, and then we extract this pk x n minus 1 term. Because we have sort of gone down in power, we follow our induction through the indices, or the powers n, to get this general expression. So if we have the projection on k of x power n, we can express that as this sort of repeated sum through all the lower powers. And then, once we have this expression, we can do an induction through k, where we assume by premise, if all of these lower projections of the exponents, all of these ones, have this low sort of power, which is vacuously true when k equals 1, then we can just apply all of our approximations. So we have this sort of inverted sum. That means that the phi of this is bounded by the maximum of the two phi values, which is just p1x. And then we have this finite summation of all these terms, which all have this phi value bounded by p1x. So their phi value is also bounded by p1x. And since this is true for every k projection p sub k, then this phi of this total thing has this bound. Proving the other direction is super easy, because we just take the first index. As for the other direction, notice that P1 is so that P1 of x times y is equal to P1 of x, P1 of y. So then P1 of x to the power of n, that is just P1 of x power n, and phi of p sub 1 of x power n, and this is the series, indexed by non-negative integers, is exactly equal to norm of p1x. Yeah, so since we have this bound on every projection, then that bounds this phi. For the other direction, we use the fact that this p1 is actually multiplicative. I think I don't have a proof of that somewhere clearly. We can probably put it in our first section if we would like. It's not too difficult actually. It's kind of straightforward. But p1 does happen to be multiplicative with the Dirichlet product. So our x times y, this is just this multiplicative property. So if we have p1 of x power n, that's actually just p1 of x and then to the power of n. So of course, if we take this phi of this series p1 of x power n, you just pull this exponent out, and it's the same as this series right here, which is just p1, some constant to the power of n. And the phi value of that is exactly p1 of x. And that gives us the other direction. Giving us equality, and that's the proof for that. Yeah, okay. I'm just rewording some stuff here now. Interesting. Okay, that's for that proof. What we want to do though is we want to include this multiplicative property. And I think what we can do is we can just go up, 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 all the way to actually our first section, I think. When we lay out our isomorphism, actually what we can do is actually what we can do is, so this also has the inverse function p1 in linear, and okay. a little too long. Okay, that's nice. So just sort of added here as a preliminary, and we can prove this now. So all we have to do now is actually prove that P1 is multiplicative for this, if we would like to prove that. And we can do that really quick, actually. It is very simple. So we'll just go down to our appendix A, and we can prove, so, a new theorem. So a function P1 is so, oh yeah, in every, there we go, x, y, and a, we have P1 of x star y is equal to P1 of x, P1 of y, and the proof for that is really super simple. It's one line. We have P1 of x star y is equal to the sum cross AB equals 1 of P1 of x, P1 y, sorry, no, P of x, P of y, which is just immediately P1 of x, P1 of y. This is so short, I'm not even sure if it really needs a proof. Yeah, I think I'll just exclude it, actually. It's just so... maybe actually here's what I'll do. I'll sort of comment it out. And if I feel like putting it back in, then I can later decide to do that. And that's fine. Okay. Back to where we were. Right down in... Or that's not right. Why is it doing that? Maybe that. Nope. Let's instead... Oh, I think I know what happened. It's because I put this here. Okay, let's do that instead. Oh, that's not what I wanted. How did that happen? Oh, that's why. Yay, the lawnmower is back. So I'll try that. Yeah, that's fine. Maybe, I don't know. Oh yeah, it's a much louder, I think, this time around. That is so weird. Okay, anyway, back where we were, down here. Okay, so what we've got so far is, we know, yes, okay, so we have all these. Let's turn these into lemmas instead of theorems. I think we can just do it like that, maybe? Let me check. Yeah, that's fine. Yeah, okay. And we'll go back down here. And we'll change some of these into lemmas. Which one of these do we want to change? We want to change this one. This one's going to be a lemma. Oh, that's not correct. I want it to be the other way around. It's referring to the wrong theorem. Gosh. Oh, I see, okay. Nice, okay. Oh no, that's also not what I want. Wait, what the heck? I'm trying to figure out how to format this. It really doesn't want to be formatted correctly. It's fine. Yeah, I think it's fine. Or is it? Okay, yeah, that's fine. Okay, so yeah, so this multiplicativity property, additive property, then we have this special lemma for inverting sums, and now the actual theorem. Okay, so where we're at now is we have, just like ordinary, actually, exactly like ordinary exponentials, if we just have some general object x and a, and we apply phi, that this sort of phi, and when interpreting phi as sort of the root test, in this sort of expanded thing, we actually just get it as the first the first index, the absolute value of the first projection. So really only the first index is actually the one that matters. Is sort of what we're finding out. That's a really actually powerful observation, and the thing that's interesting about it is it lets us essentially just decide immediately when our power series will converge. So remember up here we have so this is what we're setting. We're setting power series. So we have power series as just the sum of powers like normal, but instead of multiplication we have Dirichlet product. Now that we have this characterization of these exponents, and we know how to multiply two things together, and all we actually need now is just to put all the pieces together for the result. So that's exactly what we're going to do. So we have now a new theorem, and this is exciting. This is going to tell us exactly when a power series will converge. So let C be in A n sub 0 and x be in sum A, and actually we'll do x and x0. Then the power series, we have the summation n equals 0 to infinity. We have actually we'll just start with, no, this is fine. X minus x0 power n times c sub n converges if and only if phi, actually we want to have p sub 1 of x minus x0, and we'll do absolute value is less than or equal to, actually it's not if and only if, it's converges if this is less than or equal to phi of c, and it's actually 1 over phi of c, and only if, I'm going to do strict less than here, and we want to do a weak less than here. So this is sort of our nice theorem. So this is our theorem on convergence of power series. So they converge. What we want to say, there's this power series function here, and we'll have, so the summation converges if our p1, so our first projection, our first index of x minus x0 is strictly less than the reciprocal of capital phi of c, which is the coefficient series. And it converges only if this absolute value of this first projection is less than or equal to 1 over phi of c. So in other words, it will converge when it's less than, and it will not converge if it's greater than, which is actually exactly like ordinary power series, precisely like ordinary power series, which is that they converge when it's less than the radius of convergence and never if it's greater than, and then when they're equal is sort of much harder to determine. We have the same properties. Whoops. I got away from where I was. We were right here. So of course we're going to need a proof for this. But we've already done most of the work. So take the case that we have norm p sub 1 x minus x sub 0 is less than or equal to 1 over capital 5c, then we know that by our previous theorem, we have our capital phi of the series of powers, so x minus x0, power n, and this is indexed by n in naturals with 0. So we know that this capital phi of this thing, this is just exactly equal to norm p1 of x minus x0, and by the submultiplicative property of our capital phi function, we have I'm not going to do that. Our capital phi function, we have capital phi of the series indexed by non-negative integers, our x minus x0 power n c sub n as being less than or equal to norm p sub 1 x minus x0 and then times 5c. And of course, because our this thing is strictly less than, we want to do strictly less than, then this will be also strictly less than 1. So take the case that our first index projection is less than 1 over phi. By our previous theorem, these powers have this growth, and by the submultiplicative property of capital phi, we have this less than or equal to the product, which is just this one, and then times 5c, and because this is less than the reciprocal of 5c, then this is less than 1. And then we just have to use this to prove convergence. So we do have this inequality, and now to prove convergence, we can use one of our characterizations of phi. So to prove convergence, we use the second characterization of capital phi, I think. No, actually the third. The third is the one where we have a constant bounded some geometric series. So we have some, actually, for each phi greater than norm, actually, yeah, given, let's do lowercase phi equaling capital phi of c, which is, we'll do 1 over, actually, 1 over capital phi of c, which we know is strictly greater than, oh no, sorry. We want 1. Given that 1 is greater than the phi of this thing, such that we have x minus x sub 0 power n c sub n as being, and we want to do a of this thing is bounded by a times, there is actually this less than, there we go, less than 1. Actually, we can probably upgrade this. No. That's fine. Okay, we'll actually do it in 2 parts. Okay, so, oh gosh, we'll just start out with the convergence proof. Okay, so y greater than 0 such that this less than 5 less than 1, then okay, so the first part, our sort of setup here, that we're working with is, so take the case that, oh yeah, sorry, actually this is different. So we're actually going to prove compact convergence. That means it's going to converge uniformly on each compact subset. So in order to set that up, so first we want to prove convergence. So by our previous theorem, the one we just proved, we have phi of these powers of x, x minus xn, is just this first index. And by the submultiplicative property of phi, if we take this and we multiply it by the Cn series, this is less than or equal to, well, this values of phi is this, and then phi of c, so times phi of c. But because we have this being strictly less than 1 over phi of c, this is less than 1. What we want to do, I think, is we actually want to change this a little bit. We'll get into that in just a second, though. But we'll start with this mode. So we have this phi comparison. Now we just find some value lowercase phi greater than 0, and we just sort of fit that between this values of phi and 1. Because this is strictly less than 1, then of course this should be possible. We can find this phi, this real value between them. By the third characterization, that gives us our a some bound such that this script a of our series is bounded by a times phi power n for every n. But of course, our a is constant and our phi is less than 1. So now we can actually prove convergence. Actually, we can prove absolute convergence, which is nice. Give this a name. Okay, so we have our power series, so right up here. So we'll do our summation And we're actually going to do the lower bound as capital N, because we're doing an approximation. We're going to do our A function. And we're going to immediately get a bound from all of our different properties, so that we can just sort of pull this in. We get A of these, and then A of the Cn. Actually, we don't even need to go that far, I think. We can actually just leave it right like that. So we have our summation again. So we get A times phi power n. Okay, so we'll actually do n plus an m, and this will be in naturals, so that we'll have the summation n to n, and we'll do this other summation n to m, which is that, and this will be bound, 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 and then we have this, this will be n, A times the summation n equals n to infinity phi to the n. And this is a standard geometric series. And that solves to, let me think, it's phi to the power of n over 1 minus phi, isn't it? I think. Let me double check. I always forget how the indexing works on geometric series. Yeah, I got it right. Okay. I always forget if the bottom index is 0 or 1. Okay, so so there's our approximation. Actually, so this gives us a bound on each index. So yeah. So we can also, if we would like, we can do a projection on each piece of k. Doesn't really matter. I think this is probably fine. So 0 less than 5 less than 1. And hopefully this will let us prove compact convergence. So in order to turn this into compact convergence, what we actually want to do is modify this slightly. So we're doing all of these approximations to essentially show that this converges. And this only shows us convergence. It doesn't show us compact convergence. In order to get compact convergence, we can say, take any, actually, let's say, oh, let me think. Okay, here we go. So we'll say take some compact set, capital K, so that each x in our capital K compact set, and actually we want to say this is subset equal to A, our space. Each x in K has this bound Okay, so since K is compact, then it is closed and bounded. So we can find, let's call it some x in, actually we can say, actually let's, yeah, okay, so x in K such that A of x is, that's not true, actually. Let's do, we can find some B. Okay, there we go, that's what we want to do. So we'll find a bound B such that that, and also having P sub 1 of B is an element, so we can take this as the least upper bound to be, actually, yeah, B is the supremum of K, so that P1 of B minus x0, yes, okay. So we'll have this inequality, so this will be less than that, and also A of K is bounded by B. That's what we want. Okay, so what we're doing, in order to prove compact convergence, we're going to take, so we want to prove compact convergence across all x, that means uniform convergence across all x in a compact set, which satisfies this inequality. So in order to prove compact convergence, we'll take an arbitrary compact set. So take some compact set K subset to our space A, such that each x in the compact set has this projection less than, so 1 over 5. So it's some compact subset of the domain where this is true. Since K is compact, then it's closed and bounded. So we can find some B series, which is preceding or equal to 0. Actually, we can let B be the supremum of the image of A on the compact set K. Because K is bounded, then A of K is also bounded, and because A of K is a subset of our real sequence space for A, Blackboard A, then we can find this bound B to be the supremum. That'll exist. Because it's equal to the supremum and K is closed, we should have our P1 of B minus x0. This should be less than also, so it should also satisfy this strict inequality, less than 1 over 5c, and also A of K is less than B. So this means that for any n we have any n and x. Oh yeah, okay. Let me do a think. Okay, yeah. I actually don't want it to be the supreme. Let's try to remove x0 first. Actually, we'll make this a little simpler and easier on ourselves. Because otherwise it'll get really annoying. Okay, so take some compact set such that each x and k has this thing. K is compact, is closed and bounded. And then we have our bound B. This means that for any x and k, we have x, so we'll have A of x as bounded by B, so that to the n is also bounded by a of x1, and then that's bounded by a of b to the n, which is just b to the n. My submultiplicativity. Yeah, okay, so this is great. So now, by our previous theorem, we have phi, instead of this thing, we'll have just b here. Phi of this thing is equal to p1 of b, which we know is strictly less than 1 over phi of c. And by the submultiplicativity, okay, of phi, we then have phi of b to the n, c to the n. Actually, we can do, yeah, b to the n, c to the n as less than or equal to phi of phi 1 of b, phi c, which is strictly less than 1. Okay, now we can find phi greater than 0 such that this phi of b to the n c sub n is less than phi less than 1. And by the third characterization, there is some a such that this b to the n c sub n is preceding a phi to the n for every n. Okay, almost done. We can then put an upper bound on the tail sequence or a power series. So for each of these terms, we have, so we're going to make some approximations. So we have this, which is preceding, we're actually going to have so we'll have this term here, it's preceding, and we'll actually put that here. And we'll change this up a bit. So this is a of I think I have to do it this way. Okay, yeah, okay. So we have this thing by some blah blah blah. We have bn a of cn is less than or equal to this by c. Oops. Okay, I think that's right. I'll have to fix that. We have this, some multiplicativity. Previous theorem, we have 5bn is this, less than 1 over phi c, and by some blah 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 phi. We have phi of this thing, which is less than or equal to this thing times that thing, which is this thing times that, which is strictly less than 1. Now I can find this thing, put them in between. Okay, let's fix that. So B. Actually, this is fine because this is already positive. Okay, so from here we'll have this thing, and we have that, and see how that looks. That, spread it out, spread it out again, and then this will be, that should be p to the n. And then we get our phi n, a phi n, yes, okay, okay, okay. And that is simply bounded by this thing. Okay, that's cool. Let me take a look. Okay. Okay, that's great. Awesome. Okay. I think that's the whole thing this time. Okay, so we have yes, okay, so we're taking, this is our power series. And for each we're saying this will converge compactly over this domain. So for each compact subset K, which has this bounded property, it's going to be closed and bounded, so we can find B to be the supremum of A, K, and that makes the P1 of B also have this boundedness condition. Let me update this little typo here actually, because I changed that. We no longer have x0 in this proof. Okay, and then so for each composite K, we have this. Oh gosh, we have this this bound. So for each x and k, we have a of x is bounded by b. So this a of x power n is bounded by a of x and then power n, which is bounded by b power n by submultiplicativity. Gosh, every single equation turned into the edge. By the previous theorem, we have phi of b power n series as just being p1 of b, which is going to be less than 1 over phi of c. And by submultiplicativity of the capital phi function, that's phi of b power n times this a of c sub n. This is bounded by just the product. Phi of a of c is actually just phi of c. This is true because actually phi is just defined in terms of absolute values on pointwise. So we got phi of p1 of b and then times phi of c, and this is less than 1. Then we just, because this is less than 1, actually because this is less than 1, we just find some phi greater than 0 to fit in between that and 1. And by the third characterization, we can find this bounding coefficient to bound these powers. From there, we just take each one of these partial sums and we bound them in terms of, so we just apply, so A, we have subadditivity and submultiplicativity, then a power xn is bounded by b power n times yeah, just bounded by b power n. And then this b power n times a of c sub n is bounded by this capital A times phi power n. Then we just plot this a to the front as a coefficient. And because this is just all real positive, it's increasing with increasing uppercase m. So we can just take m to infinity. And because phi is less than 1 and greater than 0, this will converge to this expression exactly. And that's our uniform bound. We just have to sort of state the conclusion now. So this is a uniform bound because this applies for every single x inside of our compact set K. That's uniform convergence in K. And we just have to be clear about that. That's pretty much the whole thing. Nice. Okay. Now let me make sure I've got this condition right. Compactly generated space. I don't know if we're in that. Okay, let's see here. I'm gonna make sure this actually applies. Well, every first countable space is compactly generated. Well, that's easy. So we can just say that. Nice. Okay, so we've actually got, because we've proven compact convergence, we actually have proven that not only does it converge, but it converges to a continuous function, which is very fun. Nice, okay. So that proves that our power series converge whenever we have this condition to continuous function. We can actually, if we would like, prove that they diverge when this condition fails. And that can be similarly a little quick. So this will be the next proof that we want to write up is we've proven that in this domain it converges to a continuous function, and we prove next we want to show that if it's outside, if it's sort of in the exterior, that'll diverge. The way we can sort of visualize this domain, the way that I like to visualize it, is we can so in the sense that our space is sort of an extension of the complex plane, we can sort of think about the rest of the dimensions sort of poking out of the complex plane in different directions. And so this projection, that's sort of what this projection, this P1 projection, is the projection down to the complex plane, where we ignore all the other dimensions. And so what this is saying is that if the first projection is less than this radius, this reciprocal capital phi c, if the first projection is less than that radius, sorry, brain stopped working. If the first projection is less than that radius, then it'll converge to a continuous function. Another way of thinking about that is that the domain of the convergence is the pre-projection of the disk of convergence on the complex plane. So if it converges for a complex number input, then it sort of converges for all the stuff above that in all the other dimensions. So anything that's, projected down to that point on the complex plane. So it's kind of actually a cylinder set in a very literal sense. It's like an actual cylinder. It's a circular, a disk base, and then we have the rest of the dimensions as sort of being free. And that's the domain. That's very neat, actually. So the thumbnail that I chose for this stream is a particular equation. It's the equation is actually the formula for natural log is the Mercator series. We have n equals 1 to infinity, and in our sort of modern, our new notation, we're not going to use f, we're actually just going to use x. There we go. So this is the Mercator series. It gives us, for if x is a complex number, this will converge whenever we have the absolute value of x strictly less than 1. Actually, it'll converge sometimes when absolute value of x is equal to 1. But this function converges on the open unit disk. And you can actually prove that with root test, as long as you're willing to do, the root test on 1 over n. As long as you're willing to work out that limit, you can prove that this converges on that sort of open set disk. What's interesting for us, though, is that we now know that if this converges on the first index, on the first projection, if its projection to the complex plane converges, then it converges. So instead of having the absolute value of x being less than 1, we actually know that the domain of convergence of this function is whenever the first projection of x is less than 1. So we actually can, if we use this very limited definition, we can actually just take the natural log of these numbers if we define it in the right way. We haven't yet proven analyticity of power series, so we don't know that a definition like this sort of has all the nice properties we want. That is the direction we're going in. But I just thought that was neat. That was actually why I chose the thumbnail as this Mercator series. It's a really interesting application of all these convergence properties we have. Anyway, I think I'm gonna take a break for now. I have to eat food. But thanks for joining me on this little adventure. I think I will probably stop for today. Yeah, it's been 4 hours. So anyway, let me know if you have any questions. I'll wait a couple of minutes. Yeah, it's exciting. No one knows that this stuff exists except for me and the people that I've told, as far as I know. There's some weaker results as far as I can tell, so every now and then I'll look around and see, has anyone ever done anything like these? Yeah. As far as I can tell, I mean, I have no idea if anyone knows about any of this, but there's some limited results, like, and I think probably one of the bigger parts is that it's the notation is sort of hard to get around. The notation makes it, the conventional notation makes it not obvious that you can do all the things that we're doing. But if we just change the notation up to be a little more familiar, the proofs are actually really straightforward. Of course, it's been how long? Yeah, it's been 4 hours. Yeah. But yeah, so like there's some other ways, like if we go down, so last time we looked at Dirichlet inverse and we saw that, oh yeah, that's a good one. We can actually do this one really quick. So we now know that this sort of convergence happens. If we consider a coefficient series C sub n where it's just always 1, yeah, they are pretty analogous. And I also try to do that as much as possible. The proofs aren't that far away from how real and complex numbers work. Sometimes they get far away, but it's surprising how many similarities there are. But so for an example, so we did this sort of complicated, nebulous natural log of some sequence, but we can do reciprocals this way just as well. So if we have some Cn series just all being 1, then if we apply phi to that, it'll just be 1. So if we have, a function f of x, which is just the sum across all n of x power n, this series will converge so long as our projection p1 of x, if we take its absolute value, is less than 1. Sometimes it'll converge when it equals 1, but at least when it's less than 1, it'll converge. The fact that this function converges might not seem super obvious, like why this is important. But just the mere fact that this converges, and along with all sorts of continuity properties of cancellation and so on, you can figure out exactly what it is, and it's exactly what you'd expect it would be, because if you take f of x and you multiply it by 1 minus x, then you can just sort of expand this out, so you get the summation. Actually, rather than multiplying it by 1 minus x, you can just multiply it by x. Then you get the summation. Instead of x power n, you get x power n plus 1, but that's just f of x, right, minus 1 by an index shift. Oops. So f of x times x is f of x minus 1, but then that means that f of x times, right, if we factor out this f of x times x minus 1, that'll just be negative 1. That when we do this, it'll be negative 1. But because that's a unit, right? We have two things we're multiplying together and they equal a unit. We know that we're in integral domain. So if both of these multiply out to be a unit, then we have division. We can divide by these. So f of x is actually just 1 over 1 minus x. It's the reciprocal of 1 minus x. That means that if you want to calculate a Dirichlet inverse, you can actually just use a power series, and it converges for quite a lot of values, for all of these values where this first index is in this range. And that's not super obvious at first glance. So actually I decided I wanted to start doing this again. I mean, I always want to do this, but especially recently, because I noticed that there recently, like a couple of weeks ago, an update was made to the Dirichlet convolution page, including this formula for calculating Dirichlet inverse. But the only representation they have for this inverse is they have this, so they do have a geometric series, but they're only able to use it in the specific case where the series that they're sort of summing across has its first index exactly 0. And that's sort of the fastest possible convergence. So we have our radius of convergence is when the first index is less than 1, which is a whole lot of values. And the value that's known is that you can take it when it's just equal to 0, which is like the smallest possible radius. So I actually wanted to start making these because clearly, these aren't known. Like 2 weeks ago, this was added, and it's not, it's a much weaker version of this, which we were able to prove in 8 pages. And of course, there's a lot more. There's a lot more to this as well. Like, we don't have to only use powers of xn. We could do anything. We could do any sorts of other things. So this only tells us this inverse for these sorts of values. But because of the way that we have our complex numbers sort of play really nice with our space. So if we want to calculate, 1 over x for some value of x, we can just do 1 over x divided by p1 of x, and then multiply by p1 of x. So I'll do 1 over p1 of x, do double fraction here. So if we want to calculate, if we have some x which has an inverse, and we want to calculate what that inverse is, we can pull out this factor of p1x, which is just a complex number. Instead of subtracting, which you might normally think, you can divide by p1 of x. This normalizes, so x divided by p1 of x is now has its first index is now 1, because we've divided off the first term. So its first term is now 1, but because its first term is now 1. This geometric series can converge quite fast, and this extra term just sort of comes out. That's how they normally are calculating it, but we've seen that actually it doesn't have to be exactly perfect. We could actually, instead of dividing off p1, we could actually divide off any complex number, like c, and then we could write this as, so long as the resultant is in range, then we could just write this as how would it normally be? So we get this 1 over c on the outside, and then we sum up the powers for, in order to get 1 over x divided by c, that's 1 minus 1 minus, yeah. So then we get 1 minus x over c, power n. Let me sum that up. And so that's sort of this series where c is some arbitrary non-zero complex number. This will converge so long as we have the absolute value of p1 of 1 minus x over c, which is this term 1 minus x over c, as being less than 1. But because we can sort of pull this complex number out, because p1 is linear, that's c minus x times c, and then this absolute value comes out 1 over c. I think if c is, that's not right. I did something wrong. Oh yeah, okay. It's not reciprocal. It's just absolute value. Oh gosh. Okay, there we go. Yeah, so instead of only using sort of the perfect series where you just sort of translate it, you can use any complex number c, and you can sort of do this sort of series. And actually, it doesn't even need to be a complex number. This whole proof here, we'll have to do this times times c. You can pull that out. This whole proof here actually will work regardless of what c is. so long as this first index is true. If c is some general value, then we do p1 of 1 minus x over c. Well, that's actually just p1 because it's linear of 1 minus. So 1 minus p1. And because it's multiplicative, p1 is multiplicative, that's actually just p1 of x divided by p1 of c. And then we can multiply it through by p1 of c instead. And that'll get us this. Just like that. So even if c is not a complex number, this general series to calculate the inverse, the Dirichlet inverse of x, will work. So long as you know the inverse of c, which if c is a complex number, it's easy. But it could be anything else you know the inverse of. And so long as it sort of obeys this thing. So the first index of x, the distance between the first index of x and the first index of c has to be less than the first index of c. So it has to be closer to c than c is to 0, basically, on the first index. But that's a whole lot of values. That's quite a lot of values that you get from that. Anyway, it's exciting. Yeah, so anyhow, so next time we come around, we'll we'll get more into different sorts of series, and not just the fact that these power series do converge, which is nice. Yeah, very, very fancy. But not just the fact that these power series converge, but that they converge to a continuous function. We're actually going to prove that they converge to an analytic function, which is a stronger statement. Analytic means that any point in its domain has a power series expansion that expands to the function. So if you have a power series expansion on one point, well, that's nice. But we're actually going to show that power series themselves are also analytic, which is going to be super exciting as well. There's lots of properties of analytic functions that you get that are really powerful. Yes. Anyway, so that's it for now. That's it. The stream is done. I have to eat food. I'm really hungry. If I don't stop now, I'll never stop. Thank you very much for watching, and for participating. We'll have lots of fun next time, and yeah, so goodbye.